Hello everyone. In the last video we covered about data processing to see how is the data formatted for um, language models. In this video we will be diving into theory of FSTP and zero and sort of see a visual representation of how the weights, parameters and gradients flow. So let's dive in. So let's do a slide. So before jumping into data parallelism, let's first learn about the collective communication patterns in GPU. So first we'll start with broadcast. Broadcast is you have, let's say, 3 GPUs and you have data on one GPU and you want to broadcast the same data to all the GPUs. So this can be an example of if your 0th rank has weights but you want all the ranks to have the same weight, then you can broadcast the weights. And the second one is reduce, where you take all the inputs, all the data on all the ranks, do an operation and put it in one of the rank or a destination. This can be something like you want to report a metric, like you want to report accuracy across all the accuracy of classification, and you have data across all the GPUs, but you want to report the accuracy. So here there you have to take a sum of an average of the accuracy from all of this and then report it from rank 0 to the terminal. Also you can have all reduce, where you take in the data from all the GPUs, do an operation and broadcast into all the ranks. We will come back to an application of all reduce later. The other collective operations are gather, which is you have part of data in all the GPUs and you gather them at only one GPU. And also you can have all gather, where you have part of data in all GPUs and you gather the same, duplicate the same data across all the GPUs. So this can be helpful if you are gathering all the weights of a transformer block. Transformer is sequential, so if you want to gather all the transformer blocks in all the GPUs, so this all gather can be helpful. Scatter is you just scatter the data to all of the GPUs, or and reduce scatter is first you do some operation like you sum them or uh, uh, multiply them and then scatter the data. Also remember, like, these functions need to be commutative. uh, it supports applications like additions or multiplications. uh, it can do negative like subtraction, because uh, the communication from all these GPUs uh, are not necessarily going to be in order. Maybe this GPU sends in data first, the B GPU sends in data first, then C, then A, or it can go in any order. But as subtraction is not commutative, so these functions should always be uh, commutative commutative in nature. So just remember that. So we'll have some functions, like you just cannot do any other function. You can do functions like sum or multiplication or something. And so these are all the communication patterns. We will come back to the communication patterns and how they're used in data parallelism for sure. But yeah, these are like really fundamentals that you need to keep in mind. So let's see how does a neural network training work. So you have these weights. Let's, for simplicity, let's say you have 4 weights: w1, w2, w3 and w4. And this arrow and you have a batch. Here I'm calling micro batch, because when you go to concepts of distributed training, each device has a batch, so hence I'm calling it as a micro batch for a device. But this batch basically traverses through the entire forward, does a forward pass, goes to w1, w2, w3, w4. and after it goes through the entire uh, all the layers, then it does a with AutoGrad it does a backward pass and computes these gradients. So this gradients, the terminology of it is like this is the gradient for device 0, so this is our only device 0 for the first weight. So Giz is for this parameter uh, w1 on device 0, and this m1 v1 m2 v2 m3 v3, all these are first and second moment of ADAM-W optimizer. In ADAM-W, we keep track of these moments, the first and second moment, and which basically give momentum to our gradient updates, and we need to store, and this is like per parameter, and we need to store them all throughout the training process. So hence, when you are training a model, you have these memory requirements for weights. If you have n parameters, then you would have 2 into n, 2 into n, because so this is like BF16 or FP16, so it has like 2 bytes, so 2 into number of bytes. These are the amount of bytes of memory that will be consumed by the weights. So gradients would be also gradients are generally stored in FP32. We need high precision for them, so they would be like 4 times or like 4 bytes, so there will be 4n. Optimizers are also stored in FP32, so M1 has 4n, V1 has 4n, so per each parameter we would have 4n, 4n and 4n optimizers. And also like as you see here, the weight is in BF16, and weights but the optimizers are in FP32. So if you remember ADAM, in ADAM we update the weights based on whatever, so this, in our slide, this theta t is basically W. So when you are doing these operations, M and V are in FP32, but if you don't keep a copy of theta t2 in FP32, then there will are going to be precision errors here. So we need to have another set of weights uh, which are in FP32, and those only function to update the weights. But most of the time the weights are in BF16 while doing forward pass, because as you decrease the precision, the data movement becomes easier. So it is better, and these weights are used many times like in forward pass. So so it is better to have a copy of them in master weights. You pay some price with memory, but your forward pass would be much more faster. So these are um, uh, uh, all the details about training, and now let's next go to data parallelism. In data parallelism, we we have a micro batch concept of we we have 2 GPUs, and we want each GPU to process different micro batch in parallel. So as you can see here, it is micro batch 1 and micro batch 2, and these are my 2 GPUs that we saw earlier. So this we do a forward pass through here, micro batch 1, and then we take the concurrently micro batch 2 also does a forward pass, and then we do a backward pass for each of them. Now these gradients are only for this for their respective micro batches. So this G10, G20 are only for MB micro batch 1. So when you have to do an update, you have to sync these gradients G1 to G40 and G11 and G41. You have to 41. You have to sync these gradients. And if you remember from our communication patterns, let me go back to all reduce here. So you have a gradient here, all the gradients here, you have another gradients here. Now you need to take sum of those gradients and average them based on your world size and then broadcast them to each of the ranks. So we will use a all reduce pattern here of gradients. So basically your G10 and G11 will get added, and it's like double the gradients. So we divide by world size to take the average, and and then we do an all reduce. So as you can see here, the gradients are synced now, and now you can do your update, and each device has the right gradients. So now you can go ahead and just update the parameters. And if you see, like the optimizers are every GPU have the correct optimizers for the weights, so you can directly just go and update the parameters. So this is how naive distributed parallelism works. Some modifications that people generally do is instead of waiting for G10, G40 and G40 and G41 can be all reduced, right? So if you want to overlap communication and computation, so as soon as you get back G40 and G41, you can do an all reduce and synchronize the gradients. You can get back G4, so that as it comes to G11 and G10, you already have G2, G3 and G4. So you have kind of overlapped communication and computation. So these are some of the methods that people generally use to make this faster. But the problem still remains, like as you increase the model size, this GPUs don't have a lot of VRAM capacity, so you cannot fit all of these things in a GPU. And also we saw like this optimizers take a ton of memory. So that's why we are going to dive into Zero, which was by DeepSpeed Microsoft, and also we have some adaptation for Zero in FSDP. Uh, okay, let's start with 01. So as mentioned in the problems with data parallel, we cannot keep all the optimizers, gradients and weights in a GPU, as the model size keeps on growing and we are limited by GPU VRAM. So we need a way to shard these weights or optimizers or gradients. So in Zero we have three levels: 01, 02 and 03. So let's first discuss 01. So in 01 we have a similar setup. We have four weights: W1, W2, W3, W4, and we have a micro batch per GPU. And if you see here, the optimizers now are sharded: M1 V1 and M2 V2, and here we have M3 V3 and M4 V4. So instead of having all of the optimizers duplicated in all the ranks, you have them sharded now. So in 01 we shard the optimizers, and they are the one which takes the most amount of memory too, if you remember. So let's see how we are going to move forward. So a micro batch 1 goes through this GPU, we do a forward pass, and then we do a backward pass, and we get back this gradients for rank 0. Similarly, micro batch 2 passes through this rank and we get back the gradients. And now we need to, similarly as data parallel, we need to do an all reduce on the gradients, like G10 and G11 will be added, and as we average and then averaged, as we have a wall size of 2, we'll average them, and this G1 will be broadcasted to all the ranks. So here you can see, like after you did an all reduce on the gradients, all the ranks now have G1, the same gradients: G1, G2 and till G4. Here also G1 up to G4. Now in this GPU, as you only have optimizers M1, V1, M2, V2. So you can only update W1 and W2 here. And here you only have optimizers for M3, V3 and M4, V4. So you can only update W3 and W4. So you update W1 and W2 on device 0 and W3 and W4 on device 1. Then this on this device W3 and W4 are now stale because they are not updated because you don't have the optimizer states. So now you have to do this communication pattern called as all gather. So if you remember, I can go back to all gather here. If you see, draw parallel to our example here, W1 and W2, and you have W3 and W4. So you do a communication where you get in W1, W2, W3, W4 here, and also this GPU will send in W1 and W2 to this other GPU. So here if you when you do an all gather, this GPU will send W1 and W2 to this GPU, and this device 1 will send W3 and W4 to this GPU. So you are basically doing an all gather operation here. And if you notice here, this G3 and G4 are basically waste because you cannot update W3 and W4. So they are redundant gradients. Hence this will lead on us to 0.2, where in 0.2 we go one step more, where we shard the optimizers and then the gradients too. So we have a similar setup, one GPU, we have one micro batch, 4 weights, and the optimizers are also sharded. Now we calculate G1, G2, like in each device we calculate the gradients. And now instead of doing an all reduce, we'll be doing reduce scatter. So this reduce scatter is, we first reduce the gradients, like the G10 and G11 are reduced, we take the average, but this G1 is only sent to this device because we only have on this device we have the optimizer states. And if I go one step more, you see like G1 and G2 only are sent to this device, G3 and G4 are only sent to this device. So there is no redundancy in gradients now. And this also reduces the overhead on the interconnect switches, which transfer these weight parameters to across the GPUs. So now on this GPU you can update W1 and W2, and on this GPU you can update W3 and W4. And now again on this GPU W1 and W2 are stale, so you need to pull in from this GPU, and similarly W3 and W4 are stale here, you need to pull in from this GPU. So now you need to do an all gather. So this is how like generally try using 0.2 as compared to 0.1 because you won't have redundant gradients, and also like reduce scatter is preferred over all reduce because as you can see, like all reduce has a lot of communication overhead, you are sending in more stuff but you don't end up using it. So as model size continues to grow bigger, still we can go one step more by sharding the weights too. Like all these GPUs replicate the weights. So now in 0.3 we are also going forward and sharding the weights. So here W1 and W2 and W3 and W4 are sharded across devices, so as the optimizers, and then we now will see how the gradients are generated. But when you shard the weights, you cannot do a forward pass. You need all the weights in a GPU to do a forward pass. So for that you have to do all gather first. Here this device 0 has to pull in the weights W3 and W4, and device 1 has to pull in the weights W1 and W2 to do a forward pass. So as compared to 0 2, where you had to do a all gather at the end, here you have to do an all gather at the start. um, so you pull in the weights, all the weights, and then you do a forward pass, and then followed by a backward pass. uh, also remember uh, also remember, like, as soon as you do forward pass, you delete w3 and w4, but you need them during backward pass, so you have to pay another tax of doing all gather. This kind of sounded strange to me. Like, if you want to do um, um, while doing backward pass, you need w3 and w4. Why not just keep it after forward pass? I also like checked it. So this is the Hugging Face Ultra playbook. If you read this, during forward pass we do all gather operation for parameters when you need them. Since we discard the parameters immediately after we needed them in the forward pass, we need one more all gather during backward pass to do reduce scatter. So you have to um, do all gather on the weights again during backward pass, so you are paying extra cost. And this makes sense if you don't want to increase your peak memory. Like, if you keep the weights even after doing the forward pass, then your memory will keep on increasing. But if you have good communications, like across GPUs, then you would be fine to pay those communication overhead as compared to memory overhead, because memory is more expensive in GPUs. So uh, let's get back to here. So now you have to so you do a forward pass, then you discard w3 and w4 on this GPU. So while doing backward pass, you have to again uh, do an all gather on getting back w3 and w4 to do a backward pass, and then you compute the gradients. And also, you can see you can overlap lot of communication and computation here. So when you are calculating forward pass for w2, you can prefetch w3. So that way, like, as soon as the micro batch is ready to go through w3, you can just pass and do a forward pass. So you can overlap a lot of communication overhead and overlap communication and computation here. So now it will follow very similar process to 0 2, where you have these gradients across GPUs. Now you have to reduce scatter the gradients. You have to take G10, G11, take an average, and then send back. You have to do a reduce scatter, so each device would have G1, G2, and then you can just like update these weights. And now you don't have to do an all gather as you saw in 0 2, because the weights are already shaded. You don't need w3 and w4 now, because you have already processed the micro batch. So these are 0 1 2 and 3. Hopefully this was clear. And one more thing that we have to discuss is, are these when we shard w1 w2 w3 w4, so what are actually these? So these are not individual weights that we shard, or individual MLP layers. So if we go back to the implementation in RL2, you in when you do data parallelism with FSDP, um, so you need to provide a module which is called as no split modules. This no split module is basically, you can say, instead of w1 being a single weight parameter, like a single MLP layer, it can be composed of multiple MLP layers into one torch NN module. So if I step through this code and go to try to search no spatial module. So for Hugging Face, we have the Llama decoder layer to be the no split modules. So a transformer is basically we stack this llama decoder multiple llama decoder layers sequentially, and we pass the tokens through them. So uh, when we want to treat FSTP WinIt, we don't want to shard between, like, we don't want to divide the llama decoder layer. Each llama decoder layer should be of its own. It should not be sharded in the middle. So this no split modules ensures that let's say your transformer has 4 blocks, 4 transformer decoder layers. Then this W1 is the first transformer block, W2 is the second, and so on. So when you are sharding, you make sure that you are not sharding the between the transformer decoder layer. You have the entire decoder layer, else it can incur a lot of communication overhead or some numerical differences. We will discuss tensor parallelism and context parallelism, tensor parallelism in future lectures, where we actually shard the MLP layers. But in distributed data parallel, you need to make sure that each each decoder layer is treated as a FSTP unit.